This is the video covering Chapter 9 of Mazur's book, but it's going to be class day number 10, so we'll do worksheet 10 in class. So if you have time, you might consider looking over Chapter 9, especially the checkpoints are always valuable if you're going to look something over. And I usually recommend the concepts half of the chapter more than the equations half of the chapter. So the file is phys8slides09.pdf in the usual files area on the web page. So Mazur's Chapter 9 offers two definitions of work. If you took physics before, then the more familiar definition will be that work is, well, for a constant force, it's the force times the displacement, or for a non-constant force, it's the integral of the force with respect to displacement. But another really useful definition of work in the textbook is that work equals the change in energy of a system due to external forces. So if the energy of a system increases, the work done by the external forces on the system is positive, and if the energy of the system decreases, the work done by external forces on the system is negative. Okay, so we have that the change in energy of the system due to work done by external forces is the work done on the system by external forces. Okay, now there will be other ways for energy to escape from a system, like dissipation in the form of thermal energy, but this is due to mechanical forces. Okay, so external mechanical forces can act on the system and can do work on the system and can change the energy of the system. So when the force and the displacement of the point of application of the force point in the same direction, the work done by the force is positive. And when the force and the displacement of the point of application of the force point in opposite directions, the work done by the force is negative. This is probably most easily shown by examples. For instance, suppose a system consists of this dog toy and earth. So then that system can contain gravitational potential energy. So then I am outside of the system. So here's my hand. So the force exerted by my hand on this ball is an external force because the system that we're defining consists of only the dog toy ball and earth. So I'm applying an upward force to the ball, and if I displace the point of application of the force upward, I am increasing the energy of the ball plus earth system, which makes sense because I'm increasing the gravitational potential energy stored in that earth ball system. So here I am, I'm still exerting an upward force, but if I displace the point of application of that force downward, it's an upward force, but I'm displacing the point of application of that force downward. Now I'm doing negative work on the ball plus earth system. And as a consequence, I'm decreasing the gravitational potential energy of that ball plus earth system. It doesn't have to be potential energy that is changed as a result of doing work. For instance, you can change the kinetic energy of an object by doing work on it. But in any case, when we define a system, if a force external to that system does work, then the way we usually quantify that is we look at the point at which the force is applied, so that's the point of application of the force, and we look at whether the displacement of that point of application of the force is in the same direction as the force, as it is in this case, or is in the opposite direction as the force, as it is in this case. It takes a little bit of puzzling through. If you graph the work done by a force on an object as a function of the object's position, x, or actually really as a function of the position of the point of application of the force, then what graphical feature represents the force exerted on the object? So we said that the work done by an external force is the integral of that force with respect to the displacement, x, of the point of application of the force. So we can turn that statement around And we can say that here the x component of the force is the derivative of the work with respect to position. And if I graph work on the vertical axis here and I graph position on the horizontal axis here, for example, the x could represent the work that I'm doing on this ball plus earth system by applying this force to the dog toy and displacing it upward. And you can see that the farther upward I displace it, the more work I do. So the graphical feature of this work versus position curve that represents the force that I'm applying is the slope, because the force is the derivative of work with respect to position. So therefore the slope of the work versus position curve would equal the force. And this is like a constant force. I could, for example, pull on the end of a spring. And if I do that, I have to apply a bigger and bigger and bigger force as I displace it more and more. And actually, as we'll soon see, if I did that, I would instead get a curve which increases not linearly but quadratically as a function of how far I displace the end. So notice, so if I just imagine I'm pulling on a spring. Unfortunately, I don't have an example spring here. So if I'm pulling the end of the spring more and more and more, then the force I exert on the end of the spring, that's not the force the spring exerts on me. The force I exert on the end of the spring points this way, and I'm displacing the end of the spring this way. So I'm doing positive work on the spring. And then if I go in the other direction, then the force I'm exerting on the end of the spring still points this way, but I'm moving this way, so now I'm doing negative work on the spring. So since work equals the integral of force with respect to displacement, so work is the integral of the x component of force with respect to x, or for a constant force, work is the x component of force times the displacement, delta x. Force, therefore, is equal to the work per unit displacement. So if you look at a graph of work versus displacement, then the slope of that curve would be equal to the force. Suppose you want to ride your mountain bike up a steep hill. I'm actually going to change this question a little bit from how it's written so we can be really strict about the system concept. So it's really, I'm going to ride my bike up a steep hill and I'm going to tow my dog Bear behind me he's going to be in a little cart behind my mountain bike. And so the system will consist of the cart and my dog Bear and earth. And I've drawn a little magenta box around the system. So the bicycle and I are going to be actually outside the system, so the force we exert is an external force. So suppose you want to ride your mountain bike up a steep hill, towing your dog Bear behind you in a cart. Two paths lead from the base to the top, one twice as long as the other. So here is the short path, here is the long path, but the altitude gain is the same in both cases. So that means that the change in energy of the system in both cases will be mgh, where h is the altitude gain and m is the mass of Bear and the cart. Okay, so this is like, it's the mass m of the dog and the cart together. So compared to the average force you would exert if you took the short path, the average force you exert along the longer path is, so I'm going to say, if this equals let's say the average force times basically the distance traveled, the displacement, then they have to multiply to the same product. Okay, so basically this change in energy has to equal the force that I exert. Now this is going to be, in one case this is the x direction, and in the other case this is the x direction. So the x direction will just be the direction I go up the hill. So if I get the same energy gain by following a path which is twice the length, then it must be 1/2 the average force. So if I achieve the same energy gain on two paths, but one path is twice as long, then since this product must be the same, if this displacement is twice as big, then the average force must be half as big. So I would say on the longer path, I must exert 1/2 the average force. So I think I like answer C here, Charlie. And by the way, you can imagine how hard you have to press down on the pedals on average to make the bike go up one path versus the other. And you might remember from your days as a little kid biking up big hills, did you ever zigzag up a really steep hill on your one-speed bike? Or maybe if your lowest multi-speed bike's lowest gear was not quite low enough, you'd zigzag to make the path longer so that you can still make it up the hill without exerting too strenuous a force on your pedals. By the way, this scenario is not as unrealistic as you might think. I actually used to tow my previous dog, Alfie, around behind my bicycle on a little cart, as you can see in the photo. And there we are, Alfie and I on a bike ride. A piano mover raises a 100-kilogram piano at constant speed using the pulley system shown here, which is actually called a block and tackle. With how much force is she pulling on the rope, ignoring friction? And then you can take G as approximately 10 newtons per kilogram instead of 9.8 newtons per kilogram to make the math simpler. So if you look carefully at this block and tackle contraption, you'll see that if the rope over here moves down by 2 meters, then the piano actually moves up by only 1 meter. Okay, that's kind of tricky, but you see because the rope is doubled over here, so in order to make the piano go up 1 meter, you pull this rope down 2 meters. And that's so-called, that gives you a mechanical advantage. That's like a 2-to-1 mechanical advantage. So then, if you say that the force that she is exerting on the rope is F, okay, so she is exerting a force F on her end of the rope, then you know that, okay, so then you suppose that she pulls her end of the rope down a distance D, and as a result, the piano goes up a distance, let's say delta H. So then you know that the change in energy of the piano plus earth system is mg delta H, and you know that the work she does is this force times this displacement. And then we know, just from the configuration of this block and tackle system, that D is 2 delta H. So then that gives us that, let's see, so that gives us that mg delta H is the force times 2 delta H, and that gives us that the force is mg over 2. Okay, and so the mass of the piano is 100 kilograms, so multiply that by G and you get 1,000 newtons. That would be 1,000 newtons divided by 2, or 500 newtons. So instead of having to lift the piano's entire 1,000 newton weight, she only has to lift half of it. She only has to lift 500 newtons, or like basically pull it down with the rope. So this allows you to lift an object that in principle is more massive than you are, thanks to this mechanical advantage. So like I could exert in fact, suppose that her mass is only a little more than 50 kilograms, but less than 100 kilograms. If the rope weren't doubled up on this side, there's no way she could lift it. She'd just pull herself up into the air. But using the block and tackle, she actually can lift this object that is more massive than she is because the rope is doubled up on this side. So she pulls down twice as far with half the force, and then this end of the block and tackle pulls up. Yeah, she pulls down twice as far with half the force, and the block and tackle pulls up kind of 1 unit of distance with 1 unit of force. So the force here only has to be half as big as the force here because the distance moved here is twice as big as the distance moved here. So that's kind of a neat trick. So again, a block and tackle is a contraption using pulleys that gets you a so-called mechanical advantage. So because you move this a distance d, and the result is that the big massive object moves up a distance d over 2. So if you say, well, the work done here is the same as the work done here, then a small force times a large displacement equals a large force times a small displacement. So it's possible for the person to exert a force, in this case, which only equals half of the weight of this large object in order to lift this large, massive object. And I'll show you an example of my lifting myself up in just a minute. This is a 2-to-1 mechanical advantage, and you can get maybe a 4-to-1 or 6-to-1 mechanical advantage with more elaborate block and tackle devices. So with this 4-to-1 mechanical advantage of the block and tackle, it was pretty easy for me to lift Mary. And okay, if there's no danger, it's not physics. And it's also pretty straightforward for Mary to lift herself.
Almost there.
So you can see that this is, it takes some effort, but it's a lot less effort than climbing a rope by yourself with just your hands. So it's basically about a quarter the effort. So with a block and tackle, maybe you can even be your own bouldering partner. Oh, maybe I'll try it. All right, it's still rolling? This has never been tried before by me. Let's see. You're saying I want to keep one arm out this way.
Because then you're keeping your body up.
Oh.
Instead of flipping upside down the way I did the first time.
And Mary's going to teach the course if I fall and break my head. Okay, well, let's see if I am able, using this block and tackle, and this is a 4-to-1 block and tackle. So assuming that the rope doesn't stretch and that there's negligible friction in the system. So the force exerted by the block and tackle on the cart holding Mary should be 4 times as big as the force that I exert on this rope. So if I exert a force of 10 newtons on my end, then that block and tackle actually lifts the Mary and cart system with a force of 40 newtons. And one way to see that is, in order to make Mary go up, let's say, half a meter, I would have to pull my end of the rope down 2 meters, and then the work is the same. So a small force times a big displacement is the same amount of work as a big force times a small displacement. Let's see if we can make Mary go up.
Oh yeah, I'm up.
Mary is up. So somehow my arms would have to exert a force equal to my weight plus the cart's weight if we didn't have the block and tackle. We just had a single pulley. But we have this 4-to-1 block and tackle, so I can pull downward with a force that is only a quarter of the force required to lift me up. And so then you'll see actually that I pull the rope, I move the rope down, let's say about a meter, and I'll go up about a quarter of a meter. Amazing. I can lift myself up by my bootstraps using the block and tackle. And you can see I don't really even have to strain that much. So this sort of lever, the mechanical advantage of the block and tackle means I can lift my own weight plus the cart's weight without really even, well, okay, it takes some effort, but it's not a huge amount of effort. You don't see me grimacing quite the way I was when I was climbing up the rope to the top of the classroom. So that's a 4-to-1 mechanical advantage with a 4-to-1 block and tackle. You could think for a minute, what would you do if you wanted like 100-to-1 or 1,000-to-1 mechanical advantage? And I'll show you in a moment one way you could do that. You might wonder how you can get a really huge mechanical advantage. One way is to use like some system of interconnected gears. Another way, with like a big gear ratio, which is kind of what you do with your bicycle. Another way actually is to use an incompressible confined fluid. So a bottle jack or a hydraulic jack is an example of a way that you can apply a relatively modest force and lift an absolutely enormous weight. And I might have a demonstration of that too. One other way to get a mechanical advantage is to use a confined fluid. So using a hydraulic jack, if you use a small piston to push on a fluid, and then you have a big piston having the fluid push on some other object, the work done by having the small piston, the piston of small diameter, travel a large distance, displaces the same volume of fluid as having the large piston travel just a short distance. So the volume of fluid moved by the slender piston moving a long distance is the same as the volume of fluid moved by the wider piston moving a shorter distance. And then we get this same mechanical advantage of a small force applied over a large displacement versus a large force applied over a small displacement. Let's see what this does. So if I move this end of this rod back and forth 30 centimeters, okay, so each time I push this, so lifting it up doesn't really take any effort, but pushing it down, if there's something heavy here, pushing it down takes some effort. So that this force is multiplied by a displacement of about 25 centimeters. So to go 2.5 centimeters. So we're starting out at about a half, so let's say when we get up to about number 3 here. So 1, 2, 3, 4, 5, 6. It seems like 6 strokes would go up 2.5 centimeters, so it would be 60 strokes to go up 25 centimeters. So I think this is roughly a 60-to-1 mechanical advantage. So this seemed to be a 60-to-1 ratio, and this is a pretty small bottle jack. You can get much bigger bottle jacks, and I actually used a much bigger bottle jack than this with my dad to lift up part of our house once. So it's kind of a fun, maybe slightly frivolous illustration of what a confined fluid can do to get you a gigantic mechanical advantage. There is a huge log, like with this kind of diameter, and you can see a side view there. And basically I have a bottle jack on its side, which is it's a mechanical log splitter. And then you can see after cranking that handle several times with a force that is modest enough for me to apply all by myself, I split the log in half. And you can see the little piston pushing out to split the log in half. And you can see that afterward the log is split into 2 pieces. And you can even see a witness to all this action, my former dog Alfie, watching from a safe distance. And then you can see after a few more iterations, this gigantic log is split up into manageable pieces. So, and again, what's happening is that piston that's pushing against the log moves just a tiny bit as a result of my moving the handle back and forth a very large distance. So I move the handle back and forth many times, like a meter or so back and forth, and as a result, that piston moves maybe just a centimeter. And so it's a very large mechanical advantage, like it might be like 100-to-1. A spring-loaded toy dart gun is used to shoot a dart straight up in the air, and the dart reaches a maximum height of 8 meters. The same dart is shot straight up a second time from the same dart gun, but this time the spring is compressed only half as far before firing. How far up does the dart go this time, neglecting friction? Ooh. Okay, so this is an excuse for us to learn something about, so we learned earlier that the potential energy stored in the gravitational force was mgh. And now we're going to learn that the potential energy stored in a spring, I could call that S for spring, I might call it E for elastic. Okay, so we have like kind of an elastic potential energy. And this turns out to be 1/2 K x minus x relaxed squared. So it's proportional to the square of how far you compress the spring. And actually, if you want to, we could prove that. Maybe we can make it a digression to prove that. So here is start of digression. So in the case of gravity, we have the force that we would have to exert is mg, and we could do a certain amount of work, which is integrating, okay, let's say the force in the fx direction that we have to do to oppose gravity. So we're going to push an object upward. Here's an object of mass m, and I'm going to apply an external force to push it upward, and I'm going to lift it upward by some distance h. So I'm going to start at x equals 0, and I'm going to find my way up to x equals h, and I have to apply an upward force mg to oppose the weight of, to basically balance the weight of this object in order to lift it up. So I'm going to go from 0 to h, and I'm going to integrate dx in this constant force mg, and the result is mg h. Okay, so that's gravity. So if I do the same thing instead on a spring, then the force I have to exert is k times x minus x relaxed. Okay, so what does that mean? That means, like, here's my spring, and here is x relaxed, and then I'm going to pull. I'm going to exert some external force which pulls the end of the spring this way. We're going to say the x-axis points that way, and we're going to say how much work do I do in order to, on this system that consists of the spring with my external force that I'm using to pull, in order to extend the force out to some later position x. Okay, so then I can do a certain amount of work, which is the integral from 0 to, let's call it big X. I'm integrating dx, and here's the spring constant k, x minus x0, and that is 1/2 k x minus x0 squared. So I take this x minus x0 and I integrate it with respect to x, and I get 1/2 x minus x0 squared. And I'm going to evaluate that from 0 up to x. So I guess the answer ends up being 1/2 k big X minus x0 all squared. Okay, so the potential energy stored in a spring is 1/2 k x minus x relaxed squared. That was a digression, so you might have skipped that digression if you wanted to. So returning to this problem, we have that the energy initially stored in the compressed spring of the dart gun gets turned into the gravitational potential energy of the dart at its maximum altitude. So initially we have somehow we have energy stored in a compressed spring here, and then at some time later the spring is relaxed and the dart has reached some maximum height h. And so then this is this is sort of how far the spring is compressed. So it seems like we have 1/2 k times how far the spring is compressed squared has to be turned into mgh. And if it's the same spring, but we compress the spring only half as far, then it seems like we would have 1/2 k, and then so delta x over 2. We're compressing only half as far. And what do we get on the right side? So this is going to turn out to be mgh over 4, because you take the 1/2 on the left side squared and you get a 1/4 on the right side to make everything equal. So if we compress the spring only half as much, that's 1/4 as much stored elastic potential energy. Therefore, we'll get 1/4 as much gravitational potential energy at the peak altitude. So we'll go to 1/4 the total height. So I think if we initially went up to 8 meters, instead we'll go up to only 2 meters. So we compressed the spring 1/2 as far as we originally did. The result is that we get only 1/4 as much spring energy stored. And then, so that will be converted into 1/4 as much gravitational potential energy, which means 1/4 the height. Isn't that tricky? In this slide, the velocity of an object as a function of time is shown in the figure. And the question is, over what intervals is the work done on the object by some external force which causes the object's velocity to change, positive, negative, or 0? So if we look, so for instance, from A to B, is the work done by there's some external agent which is causing the velocity of this object to change. So we can go from A to B, we can go from B to C, C to D, D to E, E to F, and F to G. And you know that the work done by this external agent is the average force exerted in the x direction by that external agent times the displacement of the point of application of the force. So we can take that to be the displacement of the position of the object. And the displacement of the position of the object is proportional to the velocity of the object. So if the velocity is negative, then the object was displaced in a negative direction. If the velocity is positive, then the object was displaced in a positive direction. Here's velocity versus time. Meanwhile, the force, which is responsible for this change in velocity, so remember, a change in velocity with respect to time is acceleration, and force equals mass times acceleration. So the force that's being applied must be proportional to the change in velocity between the two time intervals. So we can say, okay, what is the sign of the displacement during the interval from A to B? So the sign of the displacement must be the same as the sign of the velocity. So between A and B, the velocity is negative, so the displacement must be negative. Between B and C, the velocity is positive, so the displacement must be positive. And between C and D, the displacement is also positive, so the velocity is positive, so the displacement must be positive. Between D and E, the velocity is always negative, so the displacement must be negative. Between E and F, the velocity is always negative, so the displacement must be negative. Between F and G, the displacement is always negative, so the velocity must always be negative. And then we can ask, well, what about the force? Okay, so the force is proportional to the acceleration, and the acceleration is proportional to the change in velocity. So then let's look at the sign of the change in velocity. So from A to B, the velocity increases. So that's a positive change in velocity. From B to C, the velocity increases. So that's a positive change in velocity. So that's a positive acceleration, since it's a positive change in velocity, and therefore it's a positive force applied to the object. From C to D, the velocity decreases. So that's a negative change in velocity, so it's a negative acceleration. So it must be a negative x component of force applied to cause that change. From D to E, the velocity decreases. So that must be a negative change in velocity, a negative acceleration, a negative x component of force. From E to F, the velocity increases. So that's a positive change in velocity, a positive acceleration, a positive x component of external force. And then from F to G, the change in velocity is 0. So then we take this times this. This must be negative work. This must be positive work. This must be negative work. This must be positive work. Negative times negative. That's interesting. This must be negative work, and this must be 0 work. So that's kind of tricky. I think you're going to work through that same problem or one just like it. But basically, in this interval, you see the displacement must have been negative, and the acceleration, therefore the force, must have been positive. So this must be negative work. Here, the displacement is positive, and the acceleration is positive. So the force must be positive. That's positive work. Here, the displacement is positive, but the acceleration is negative. So the force is negative. So that's negative work. Here, the displacement is negative and the acceleration is negative, so the force is negative, so that's positive work from D to E. A, B, B, C, C, D, D, E, yeah. From E to F, the displacement is negative, but the acceleration is positive, so the force is positive, so that must be negative work. And then from F to G, the acceleration is 0, so the force is 0, so that's 0 work. That's kind of tricky also. Stretching a certain spring 0.1 meter from its equilibrium length requires 10 joules of work. How much more work does it take to stretch this spring an additional 0.1 meters from its equilibrium length? Remember that the energy stored in a compressed spring or a stretched spring is 1/2 times the spring constant times how far it is elongated or compressed with respect to its relaxed length squared. So when we stretch the spring 0.1 meters from its relaxed length, we say that is 10 joules of stored energy in the spring. So if you're going to stretch it twice as far as originally, then if you take this x minus x0 and you double it, then you must quadruple the stored energy in the spring. So it must be a total of 40 joules stored in the spring when it is stretched 0.2 meters total. You see, so if it's not stretched, there's no elastic potential energy. If it's stretched by, let's say, 1 unit here, then that is 10 joules of stored energy. And if you compress it, if you stretch it twice as far, you must store a total of 4 times as much energy. So what that means is to go from here to here required an amount of work equal to 10 joules. And so to go from here to here must require an amount of additional work equal to 30 joules. That's pretty tricky because it was already here. So we only had to go from point 1 to point 2. We didn't have to go from 0 to point 2. So I think going from point 1 to point 2 required an additional 30 joules of work. So I think the answer is D, delta, an additional 30 joules of work, because it took 10 joules to go from 0 to point 1, and it would take a total of 40 to go from 0 to point 2, but we were already at point 1. So to go from point 1 to point 2 would therefore take an additional 30 if the starting point is that we're at point 1. A block initially at rest is allowed to slide down a frictionless ramp and reaches a speed v at the bottom of the ramp. To achieve a speed 2v, twice as big a speed, at the bottom, how many times as high must the new ramp be? And I think this is a transformation of energy problem. So we have, initially we have mgh1 at the top of the hill, and by the time we get to the bottom of the hill, that has been transformed into 1/2 mv1 squared. And now we want to have another hill which is higher, mgh2, and that's going to be transformed into 1/2 mv2 squared, but we know we want v2 to equal 2v1. So this is 1/2 m 2v1 squared. which somehow must equal 4 times 1/2 mv1 squared. So I think that somehow must equal 4 times mgh1 must equal mgh2. Let's see if I can try that more neatly. mgh2 over mgh1 equals 1/2 mv2 squared over 1/2 mv1 squared. So h2 over h1 must be v2 over v1, the quantity squared, and you know v2 is 2 times as big as v1. So this is 2 squared, which is 4. So h2 must be 4h1. So we must need to build a new ramp which is 4 times as tall as the initial ramp in order to achieve twice the speed at the bottom. At the bowling alley, the ball feeder mechanism must exert a force to push the bowling balls up a 1 meter long ramp, but it's a diagonal ramp. The ramp leads the balls to a chute which is a 1/2 meter above the base of the ramp. About how much force must be exerted on a 5 kilogram bowling ball as it goes up the ramp? So somehow this force exerted over this displacement must be enough to increase the ball's plus Earth system's gravitational potential energy from here up to here. So we're going to say the change in gravitational potential energy is mg times the gain in altitude, and that increase in the gravitational potential energy of the system is going to be equal to the work done as we displace the ball by whatever external force is pushing the ball. And that is going to equal here, this is my x-axis, this diagonal thing. So it's going to be the force in this diagonal x direction times the displacement in this diagonal x direction. So we are saying that mgh is this unknown force times this known displacement. And then all the values are known except for the force. So we're saying 5 kilograms times g, which we're taking to be 10 newtons per kilogram, same as 10 meters per second squared. And then the height gain is going to be a 1/2 meter. And that is going to equal this unknown force times 1 meter. Because, see, we're pushing diagonally 1 meter with some unknown force, and the result will be that we increase the ball's gravitational potential energy, the gravitational potential energy of the ball Earth system, by mg times a 1/2 meter. So it seems like the answer is going to be that this unknown force is 5 kilograms times g, 10 newtons per kilogram, and then times a 1/2 divided by 1, so basically times a 1/2. So that seems like it's going to equal 25 newtons. So I think I like answer D, delta here, 25 newtons. Let's just check that. 25 newtons times 1 meter is going to be 25 joules of work. And then 5 kilograms times g, so that's 50, and then times a 1/2 meter, that's going to be 25 joules increase in gravitational potential energy. Okay, so 25 joules of work results in 25 joules of increased gravitational potential energy. So that adds up. Suppose you drop a 1 kilogram rock from a height of 5 meters above the ground. When it hits, how much force does the rock exert on the ground? Oh, and you can take g, approximately equal to 10 meters per second squared. So when the rock hits the ground, how much force does it exert on the ground? Well, so we can figure out how much kinetic energy it has just before it hits the ground. But then we don't know over what short distance it loses that kinetic energy. So, the rock starts out up here, and then it's going to hit the ground down here. And when it hits the ground, it's going to be, moving pretty fast in the downward direction. And then somehow it's going to sink into the ground just a little bit as it comes to a stop. But we actually don't know just how far it sinks into the ground, just a little bit as it comes to a stop. So actually we have no idea how much force the rock exerts on the ground because we don't know what the little distance is over which it stops. So we actually do not have enough, here we go, impossible to determine without knowing over what distance the rock slows when it impacts the ground. You see, so we do know, here's mgh, and it becomes 1/2 mv squared. We know how much 1/2 mv squared there is corresponding to this mgh, but then somehow that has to be some force exerted by the ground over some displacement is going to absorb that kinetic energy. And we don't know how big that displacement is. In other words, we don't know how far the rock sinks into the ground. So without knowing that, there's no way for us to know how big the force is. This is very similar to a problem we did just a moment ago. The velocity of an object as a function of time is shown in the graph. So it's like the x component of velocity on the vertical axis and time on the horizontal axis. Over which time intervals is the work done on the object by whatever external force is accelerating the object, positive, negative, or 0? Hint, make a table showing the sign of acceleration, which therefore is the sign of the net force, and the sign of the displacement, and the sign of their product for each segment. Okay, so let's go through and do that. So from 0 to 1, the velocity, the x component of the velocity is always positive, therefore the displacement is positive. And the x component of the velocity increases, therefore the acceleration is positive, therefore the force must be positive. Therefore the sign of the work must be positive. From 1 to 2, it seems as if the velocity is positive, therefore the displacement is positive. But the change in velocity is 0, so the acceleration is 0, so the force is 0, so the work is 0. From 2 to 3, the velocity is positive, so therefore the displacement is positive, but the change in velocity is negative, so the acceleration is negative, so the force causing that acceleration is negative. So the work is a product of these two, which must be negative. Well, because, remember, work is the force times the displacement. So we're checking the sign of this times the sign of this. And then from 3 to 4, it seems like the displacement is negative because the velocity is always negative in that interval. Right, it's below 0. The velocity is below 0, so the displacement has to be negative. But the velocity is decreasing, therefore the acceleration is negative. So then negative times negative is positive, so that's positive work. Going from 4 to 5, the velocity is always negative, so the displacement must be negative. But the change in velocity is 0, so the acceleration is 0, so the force is 0, so the work is 0. Going from 5 to 6, the velocity is always negative, so the displacement must be negative. But the velocity is increasing, therefore the acceleration is positive, so the work must be negative. Interesting. From a bridge at initial height h above the water, I release from rest an object of mass m, which is attached to a bungee cord, which basically is a spring, whose relaxed length is L0, and it has a spring constant K. Which equation correctly expresses assuming that no mechanical of energy is dissipated into heat. Yeah, so assuming no mechanical energy is dissipated into heat. So it's a closed system and somehow we're able to account for all the energy. The speed v final of the object when it reaches the water surface. Okay, so one end of the bungee cord is tied to the bridge. So the cord is initially slack and does not begin to stretch until the object has fallen a distance equal to the cord's relaxed length. So here's the cord all bunched up. And then the idea is, okay, so the person, the mass m, jumps, okay? And at some intermediate point, you see, the cord stretches out, so it's at its relaxed length. So this becomes L0. And this thing is moving down in the meantime. But then it keeps going, so it's going to eventually reach some, it's going to reach the water. Okay, so here's M, and it just reaches the water. So now somehow this distance must be L minus L0, right? So it seems like somehow we've fallen a distance h, but the spring has not stretched by an amount h. The spring has probably stretched by an amount, it must be like actually h minus L0. Yeah, so it seems like it's actually, this L minus L0 is the same thing as h minus L0, because it seems like here's a distance h, but meanwhile, you see, by the time we fall just a distance L0, the relaxed length of the spring hasn't stretched at all yet. And initially it's just all floppy. So we don't do any, we're not changing the potential energy of the spring until it starts to stretch, because this is a bungee cord. So initially it's just all floppy. But then here it's stretched out to its full relaxed length, but we still haven't stretched it yet. And then we stretch it, I guess we stretch the spring by a distance height minus L0. Because here's height, and then here's L0, the relaxed length of the bungee cord. So the amount that we stretch the bungee cord must be height minus the relaxed length of the bungee cord. So then let's account for energy. Okay, so in the initial state, so we're going to say E initial equals E final. So in the initial state, we have so initially we have gravitational potential energy is mgh, and we have kinetic energy 0, and we have elastic energy 0. Oh. But at the end, let's say finally, we have gravitational potential energy is 0, and we have some non-zero kinetic energy, which is unknown. And we also have some elastic potential energy, which I think we know because it's somehow given by the bungee cord being stretched this much. So I think what we can say, again, assuming that all the energy is transformed in ways we can account for, so we're going to have, initially, we have mgh. And then in the final state, we have 1/2 mv final squared plus 1/2 k. How far is the bungee cord stretched? I think it's h minus relaxed length squared. Okay, let's see if that makes sense. So here's the initial gravitational potential energy. Here's the final kinetic energy, and then here's the final elastic energy stored in the bungee cord. So it's 1/2 k, and then how far stretched it is, the quantity squared. And how far stretched is it? It's the height that we fall minus the relaxed length, because for the first relaxed length that we fall, we're just basically like unfurling the floppy bungee cord, and then it starts to stretch. So I think I like that expression. Let's see if that matches one of our choices. So mgh equals 1/2 mv final squared plus 1/2 k h minus relaxed length squared. I think I like answer F, foxtrot. So mgh is our initial energy. It's all gravitational potential energy. And then we have 1/2 mv final squared. That's our final kinetic energy. And we have 1/2 k height minus relaxed length, that quantity squared. I think I like that. This will reappear, I think, on a worksheet. A motor lifts an object of mass m at constant upward velocity v sub y equals dy by dt. How much power, power being work per unit time, does the motor supply? Okay, so power is the work per unit time, and we are lifting the object of mass m at constant upward velocity dy by dt. So one way we could look at this is to say that we have the energy of the system is, well, if we just look at the gravitation, because it's constant velocity, okay? So there's some constant kinetic energy. There's constant velocity. So the kinetic energy is going to be constant, whatever it is. And then plus mg, and I guess we're using the variable y, even though we don't really use the variable y until the next chapter. So then we could say the rate at which work is done is also the rate at which the energy of the system is changed. Okay, so the rate at which we do work is the rate at which we're changing the energy of the system. And we're not changing the kinetic energy, so that has no change. And then we can say mg, and then as those are just constants. And then here's how fast we're changing the coordinate y. So I guess this then equals mg times the velocity y. I think that makes sense. There is actually another way to look at this. You could say that it turns out power equals force times velocity. So you can say, aha, I am exerting an external force mg to lift the object, and it is being displaced at a velocity v sub y. So then once again you get mg is the force, and then v sub y is the y component of velocity. So I guess we could say that. We could also say that the energy of the system is 1/2 m v sub y squared, even though we haven't introduced the variable y until the next chapter, plus mg y, and then we can take the rate of change of that. So v sub y is a constant. I guess we kind of did that up there. So v sub y is a constant. So you could say, here, let me erase the line up here. Sorry. So we can say power. Power is the rate of change at which the rate at which we are changing the energy of the system. That's the rate at which we're doing work on the system. This first term is a constant because the mass is constant and the velocity is constant. So that's 0. And then we say mg. The only thing non-constant here is y. So that's mg dy by dt, which is just mg v sub y. Let's see what our options were over here. So power is mg times velocity in the y direction. I like that. Power is mgy. I don't like that. Power is 1/2 mvy squared. I don't like that. Power is 1/2 mvy squared. No, I don't like that. Power is the rate of change of the kinetic energy plus the gravitational potential energy. I like that. So I think A and E, alpha and echo, are both correct. So you could say force times velocity, which force is mg. Velocity is the vertical velocity. Or you could say that the energy is the kinetic energy plus the gravitational potential energy. This is constant because the velocity is constant, but this is changing because the height is changing. So, and then how fast is it changing? You see, this is a constant, but this is changing at a rate equal to the velocity. So I think, so this is a true statement because you could say force times velocity. This is a true statement because the energy of the system is the kinetic energy plus the gravitational potential energy, and the rate of change of that energy is the rate at which we are doing work on it. And then if you actually evaluate this expression, this first term is constant, the second term is just mg times the velocity in the y direction, which is the same as answer A. So answer A and answer E, alpha and echo, are both correct. A motor lifts an object of mass m at constant upward acceleration a sub y, which is the rate of change of v sub y. I guess somehow we've introduced the variable y, even though it doesn't really appear till the next chapter. How much power, power being work per unit time, does the motor supply? Oh, that's pretty interesting. So I think the way to do this is to write an expression for the energy of the system. And the energy of the system is 1/2 m times the speed squared, and I guess we're using y as the coordinate, and then plus, that's the kinetic energy, and then we have the gravitational potential energy, which is mgy. I guess we have the y-axis pointing up. So then we can say that power is the work on system by dt, which, so the rate at which we do work on the system equals the rate at which the system's energy changes, assuming that the work we're doing is the only cause for changing the energy of the system. And so then we could say, well, the mass is constant, but this is not constant. So this is, okay, so this is 1/2 m times, now you have 2 times v sub y times dv sub y by dt. That's the chain rule, right? So the derivative of v sub y squared is 2 times v sub y times the derivative of v sub y. So it's 2 times v sub y times v sub y by dt, and then plus mg, and then, so this is a constant, this is a constant, this is changing, so this is dy by dt. Now, dy by dt is just the velocity in the y direction, and dv sub y dt is the acceleration in the y direction. This is, the 1/2 cancels the 2, this is m v sub y a sub y, and then this is mg dy by dt is just v sub y, mg v sub y. So you could say that's m v sub y times a sub y plus little g. Let's see if that matches any of our candidate answers. So we could say m a sub y plus g v sub y. That looks pretty good. 1/2 m. And also, I think this makes sense also. So I think I like B and E. Yeah, so I think my answer would be golf, because Bravo and Echo are both correct. So we can write an expression for the total energy, which is 1/2 mv squared plus mg times the height. So it's 1/2 mv sub y squared plus mgy. And then we can take the rate of change of that energy, and it must be the rate at which we're doing work on the system. So we take the derivative of both terms. Okay, so power must be the rate of change of this expression. So that's answer E, Echo. And then if you actually evaluate that rate of change of that expression, you get m times v sub y times a sub y plus g. So that is answer B, Bravo. So I like answer G, golf, because I think B and E are both correct. An object is said to be in stable equilibrium if a displacement in either direction requires positive work to be done on the object by some external force. let's suppose there is some potential energy associated with every position of the object. In other words, there is some potential energy curve u of x, where x is the object's position. How do you expect u of x to change as you move the object away in either direction from its position of stable equilibrium? So I think if we associate some function u of x associated with every position, and then we start out here, and let's say this is an equilibrium position. So if we have to do positive work on the system to move it away from equilibrium, then I guess that means that we must increase its energy as we move it. And we could move it, like we could nudge it just a tiny bit. So I think this should be its potential energy, not so much its kinetic energy, because it could be at infinitesimal speed the whole time. We could just give it a tiny little displacement. So I think that somehow, if it is at equilibrium, it must be true that displacing it in either direction increases its potential energy. So I think that must imply that at an equilibrium point, so we could say this is some equilibrium value of x, I think an equilibrium point must be the local minimum of the potential energy function, you see? So I think at equilibrium, I think an object must be at a local minimum of potential energy. I think that's probably true. That seems like a pretty good statement to me. Let's see what our options are here. When displacing the object away from its equilibrium position, the positive work done on the object plus its environment by the external force causes a positive change in the potential energy function u of x. So u of x must have a local minimum at the object's stable equilibrium position. I think that makes sense. I like A. Let's see what other options are. U of x must have a local maximum at the object's stable equilibrium position. I actually don't like that, because then if you displaced it a little bit, its potential energy would be going down. So I think you would be doing negative work on it because you would be decreasing its energy. So I think I do not like B. C, the derivative du by dx must have a local minimum at the object's stable equilibrium position. No, I don't think that's true. Because, you see, here I think du by dx is negative, and here I think du by dx is positive, and here du by dx is 0. So it went, you see, du by dx went from negative to positive. So that's not a local minimum. So I don't think I like that at all. Oh, the derivative du by dx must be 0 at the object's stable equilibrium position. I do like that because, you see, the slope of this u of x curve is 0 here. So there's no need for u to equal 0 here. But I think the slope, you see, the slope of this u of x curve had to be 0 here. So I think I like that. And also, you know that when a function is at a local minimum, its slope must be 0. So I think you say du by dx equals 0 at equilibrium. I think that's true. So the derivative du by dx must be 0 at the object's stable equilibrium position. So I think I like answers alpha and delta. So I guess my answer would be echo. This is a little bit of a subtle point, but the derivative of the potential energy function with respect to position must be 0 at equilibrium. And at some point, I think we will see that the force in the x direction, let's say, for example, the gravitational force in the x direction is minus du gravity by dx. So for example, if u gravity, remember how we have u gravity is mgx, if we have the x-axis pointing up, then this would be, you see, minus dmgx by dx, which is minus mg g. Well, that makes sense. The gravitational force in the x direction is minus mg. Let's instead consider a spring. So we have u elastic for a spring is 1/2 k x minus x relaxed squared. So let's say we have x pointing to the right. So for our spring, we have x pointing to the right, and let's say here is x relaxed, and then here is x, so x is going that way. So then the force exerted by this spring potential energy, so the force exerted by the spring, I guess, so the force associated with the spring potential energy. So we have the spring elastic force, which is like the force exerted by the spring in the x direction, is minus du elastic dx, which is minus the derivative of 1/2 k x minus x relaxed squared, and that is minus so the square cancels to 1/2. See, here's k x minus x relaxed. Well, that makes sense. So the force exerted by the end of the spring in the x direction is just minus k times x minus x relaxed. You see, so that's minus the derivative of the potential energy function with respect to the displacement or the position. So we said that the force, an external force, is plus the derivative with respect to position of work done by that force. But we also say that the force in the x direction exerted by a force that can be represented by a potential energy is actually minus the derivative of that potential energy function with respect to position. So that's a little bit tricky. So force is plus d work by dx, but force is minus d potential energy by dx. Here is a kind of tricky and a little bit silly reading question whose main purpose is to get you to think a little bit harder about the definition of work. Work is the transfer of energy across a system boundary due to external forces. So work is the change in a system's energy caused by external forces. Or you could also say that work is an external force times the displacement of the point of application of that force, and you have to get the signs right. The question is, when you stand up from a seated position, you push down with your legs on the ground. So are you then doing negative work when you stand up? And to answer this question, you have to think pretty carefully about what you mean by the system. So there have been a whole bunch of answers over the years to this question. Here's one example answer. The example answer here is, in this situation, we have two systems. First, in the system of just the person, the action of standing up will result in a loss of internal or chemical energy, thereby resulting in a loss of system energy and hence positive work done by the system. Gravity is an external force which points in the downward direction because Earth is not part of the system. The person's center of mass is being displaced upward. So the point of application of the force is being displaced upward, but the force points downward. So that is negative work done on the system by this external force, which is Earth's gravity. So negative work is being done on the person, and therefore you could argue that the person is doing positive work because the person is losing energy. And in fact, from the person's perspective, some kind of internal chemical or food energy is being lost out of the system. So I think that makes sense. Now, instead, let's think about the system of the person and Earth. So for the system of the person and Earth, the action of standing up increases the system's potential energy at the expense of the person's internal food energy. So in that situation, there's no change in system energy and therefore no work is done. I think that also makes sense. That's also consistent See, in the first situation, the thing doing the work was Earth's gravity, which was external to the system. But now in the second case, we're saying Earth is part of the system, so now this gravitational force is an internal force, so then no work is done. So that makes sense. We're just converting energy inside the system from chemical energy stored inside the person's muscles to gravitational potential energy stored in the Earth-person system. That seems okay. Let's look at some other ways to answer this question. Suppose the system is me plus the Earth plus the floor plus the chair. So I start out, I have like no velocity, and of course I guess I have to move up, but then by the time I'm done I also have no velocity. So the change in kinetic energy is 0 because I have no kinetic energy initially, and in some intermediate state I have a little bit of kinetic energy, but then in the final state I have no kinetic energy. So delta kinetic energy is 0. Delta gravitational potential energy is m times g times my change in altitude. Okay, so there's some gain in gravitational potential energy. That makes sense. Gravitational potential energy increases. Then the change in thermal energy, this is another category. If you look through chapter 9, thermal energy is one form of internal energy. Let's say that there's no change. This is, maybe it's debatable, but it's not really that relevant. Okay. Then there's source energy. So the change in source energy is minus mg times my change in height. So I think that makes sense because ultimately the source of that energy was food. So basically, like, when I go from here to here, I'm converting chemical energy stored in my body into gravitational potential energy stored in the Earth body system. So source energy is decreasing. That's like chemical energy stored in me. But gravitational potential energy is increasing. So the work done is 0. So that's kind of consistent with that first answer on the previous slide. So there are no external forces. Everything of interest is inside the system boundary. See, so work really depends very closely on how you define the system boundary. So now let's try choosing a different system. Suppose the system is me plus the floor plus the chair, but it doesn't contain Earth. So now, okay, kinetic energy change is 0 because, okay, I'm not moving now, and by the time I'm done, I'm not moving. So the change in kinetic energy is 0. The change in gravitational potential energy is 0 because gravitational potential energy is not defined if Earth is not part of the system. The change in source energy, that's like chemical energy stored in my body, is negative because I did burn some calories to do that. That makes sense. Okay, so my source energy decreases. So the external gravitational force exerted by Earth on me does negative work on me. The point of application of this external force is my body's center of mass. The gravitational force exerted by Earth points downward, but the displacement of my center of mass is upward, so the work is negative. So the system, consisting of me and the floor and the chair, the system's total energy decreases. So that would seem to be the second answer on that previous slide. Let's try answering a slightly different question. So when a friend stands me up from a chair, maybe because my knees are weak today, does my friend do positive or negative work? Well, suppose the system is me plus Earth plus the floor plus the chair. So, okay, initially I have 0 kinetic energy and my friend's helping me stand up, but then by the time my friend's all done, I have 0 kinetic energy. So the change in kinetic energy is 0. The change in gravitational potential energy is positive, right? Because that's mg times my altitude gain. So that's a positive number, the change in gravitational potential energy. We're not going to worry about the change in thermal energy. The change in source energy is 0 because it wasn't my cashew cereal that did the work. It was my friend's cashew cereal. My friend took food energy to help stand me up. It wasn't my food energy, it was my friend's food energy. So it's 0 for me. So then the work done on me is mg times how far my center of mass was displaced. So that's positive work done on me by my friend. So my friend applies an upward force underneath my arms. the point of application of the force is displaced upward. So that's positive work done on me by my friend. Now, let's include my friend as part of the system. So when a friend stands me up from a chair because my knees are weak, how does my friend do positive or negative work? So if the system is me plus the earth, plus the floor, plus the chair, plus my friend, change in kinetic energy is 0 because initially nothing is moving, and in the final state nothing is moving. The change in gravitational potential energy is positive because I have this altitude gain and earth is part of the system. Okay, we're not going to worry about the thermal energy. The change in source energy is negative because my friend, who's part of the system, had to burn some cashy cereal calories, some kind of food stored chemical energy to lift me up. So the work is 0. There's no external force. Everything happened within the system. So the work is 0. So let's go back to the original reading question. So when you stand up from a seated position, you push down with your legs. Does this mean you do negative work when you stand up? I think the work done on the system by my legs is either positive if you consider my legs to be external to the me plus earth plus floor system, and my legs are supplying the energy to lift me. So if you take my legs to be outside the system, so you see the legs are kind of like my friend, then my legs are doing positive work because my legs are pushing me up, and the center mass of my body is being displaced upward. So my legs are pushing me up, and so my legs are exerting an upward force on me, and my legs are displacing the rest of my body upward. Or you could say that the work done on the system by my legs is 0 if my legs are part of the system. You see, my legs are playing this role of my friend, because then it would be an internal force. The one way we got a negative answer is the case in which Earth was not part of the system. So if Earth was not part of the system, gravity was an external force. So if Earth was not part of the system, we found the external force of Earth's gravity did negative work on me because the gravitational force points down. My center of mass is being displaced upward, so Earth's gravity is doing negative work on me. Makes sense? If you treat gravity as an external force, okay, so there's no gravitational potential energy, gravity is just an external force. See, the kinetic energy of the ball here is 0. I drop the ball, and then the kinetic energy of the ball goes from 0 to a positive value. So this is Earth's gravity, an external force, doing positive work on the ball. So if we do the opposite, and if we lift the ball up, then if Earth is not part of the system, then Earth's gravity is an external force doing negative work. Here, it's an external force doing positive work if the ball goes down, and it's an external force doing negative work if the ball goes up. So that kind of makes sense. I was pushing Earth downward away from me. I lost energy. So even in this case, where the work done on me was negative, the work done by me was positive. So the key point, what you call work, depends on how you define the system. So this is a little bit, it's kind of interesting to puzzle through. So some key ideas from Chapter 8 about force and Chapter 9 about work. So impulse is change in momentum delivered by an external force. Impulse is transfer of momentum across a system boundary. So force is the rate of change of momentum with respect to time, and impulse is here the integral. I guess impulse is actually a vector, so the x component of impulse is the integral of an external force in the x direction, external with respect to time. Yes, remember, impulse has the same units as momentum. So impulse is transfer of momentum across a system boundary, and force is the rate of change of momentum with respect to time. And if you integrate an external force in the x direction with respect to time, you get the impulse in the x direction. So by contrast, force in the x direction, let's say, is the derivative with respect to position or with respect to displacement of work, and work is the integral of an external force in the x direction with respect to displacement x. So if you integrate force with respect to displacement or position, you get work. If you integrate force with respect to time, you get momentum, or equivalently, you get impulse. So work is the transfer of energy across a system boundary. Impulse is the transfer of momentum across a system boundary. Either one requires an external force. So you integrate an external force with respect to time, you get impulse. You integrate an external force with respect to displacement or position, you get work. If you have a force exerted by a spring or a force exerted by gravity, then the force exerted by the spring or the force exerted by Earth's gravity in the x direction is minus the derivative of that potential energy function with respect to position. So force is positive, the derivative of work with respect to position by an external force. Force is minus the derivative of a potential energy function with respect to position. Although you kind of have to think carefully about what is exerting the force. The change of energy of a system is the flow of energy into the system, which then equals the work done on that system. So work is the change in the energy of a system, which equals the change in kinetic energy, plus the change in potential energy, plus the change in source energy. Source energy is like energy stored in chemical fuel, energy stored in food in your body, energy stored in a battery, and then plus the change in thermal energy. So, like if kinetic energy gets dissipated into thermal energy, like the basketball hits the ground and some of that kinetic energy is turned into thermal energy, then that's the way you can account for it. As long as you're able to capture that thermal energy, maybe you don't let the thermal energy escape, then you can account for that thermal energy by saying the thermal energy of that system. Like maybe the room, like I bounced a basketball and the result is that the kinetic energy is dissipated, but the room gets a little bit warmer. So that's like increased thermal energy. So notice that work is to energy as impulse is to momentum. In other words, work is the transfer of energy across a system boundary due to external forces. Impulse is the transfer of momentum across a system boundary due to external forces. So here's some stuff from the equation sheet for chapters 8 on forces and 9 on work. So for an external force acting on a system in one dimension, and it also has to be a non-dissipative force, this is not true for friction, work is the integral of the x component of force with respect to position x or displacement x. So work is the integral of force by dx. This is the force in the x direction. If the force is constant, then you can just say the work done by that external force is the x component of the force times the displacement of the point of application of the force. So you can just say work is the x component of the force times delta x if it's a constant external force. Power is the rate of change with respect to time of the energy of a system. And then you can also say that it is the rate at which work is done on a system. Okay, since work is the transfer of energy into a system by external forces. It also turns out that power is force times velocity. So if you have an external force in the x direction, and then the point of application of that force is being displaced in the x direction, then you can have the power delivered by that external force is the x component of force times the x component of velocity. Then on this side, Gravitational potential energy. So if we define the x-axis to point up, then gravitational potential energy is mgx. Next chapter we'll define the y-axis to point up, so gravitational potential energy will be mgy, or sometimes I like to write mgh, where h is height. But if we do write mgx here, then the gravitational force in the x direction, you see, is just minus the derivative with respect to x of this potential energy function. So it's minus mg, because this is a constant, this is a constant. So the derivative of x with respect to x is 1. See, so this is minus mg. So force is minus the derivative with respect to position of potential energy. For a spring, we have the potential energy stored in the spring is 1/2 k x minus x relaxed, that quantity squared. And by analogy, you see, if we take the derivative of this expression with respect to the position of the end of the spring, we get the force in the x position exerted by the spring on the load, which is minus k times x minus x relaxed. So the force exerted by the gravitational force is minus mg in the x direction, where x points up because the force points down. The force exerted in the x direction by the spring on the load is minus k x minus x relaxed. So in this case, x points to the right and that force points to the left if x is bigger than x relaxed. So that's all I have for chapter 9. So there are a lot of new quantitative results in chapters 8 and 9 about springs, about gravity, about work, about potential energy, about power. So we have both the force and the potential energy associated with gravity and associated with springs. We have power being the rate of change of energy. We also have power being force times velocity. We have work being change of energy across a system boundary due to external forces. And that also means that work is the integral with respect to position of external force. Then we have impulse is the integral with respect to time of an external force, and impulse is the transfer of momentum across a system boundary. So there's a lot of new stuff to work with in chapters 8 and 9. So we'll practice all of this in the worksheets.